Hello everyone and welcome to this week's lecture on open channel flows. In this lecture we will talk about the open channel flows and what are the basic fundamental concepts of open channels and their different types. We will also look at different terms used in the design of open channels, and we will look at some governing equations for the open channel flows. So at the end of this lecture, you should be able to understand and identify open channels and perform fundamental analysis of open channel flows in terms of flow depth and flow through an open channel. So open channel hydraulics is a subject of great importance, not only to chemical engineers, but also to civil engineers and mechanical engineers. And most of the time, if you are working in open channels, you work as a group with civil engineers and mechanical engineers. And these open channels deal with flow having a free surface in a channel constructed, for example, for water supply, irrigation, drainage, sewers, or power generation. And you can also have natural open channels, for example, streams and rivers. So an open channel is a duct or a system in which the liquid flows with a free surface. Okay, so that is the definition of open channel flow. And here you can see that you have this tank here, and this tank you have the fluid is flowing through this container or this tank, and it is maintaining a free surface where the atmospheric pressure is applied. And this flow can be characterized as open channel because it is maintaining a free surface. Okay. Similarly, you can have open channel flow inside a circular pipe if you are maintaining a free surface, for example, in this case here, and you have this atmospheric pressure applying on the surface of this liquid. Okay. So if this pipe or this circular shape is completely filled, as such there is no free surface, we will call it a pipe flow. But if there is a gap inside the pipe and you have a free surface with the atmosphere, we will consider it as an open channel flow. Okay. So here on this slide, I have put some links to some interesting videos to bring to your attention that what kind of open channel flows are there, and also what are the for example, importance of open channel flows, for example, for flood prevention. And if you have or if we don't have an excellent flood prevention system, it can cause massive destructions. Okay, so these are just some videos that you can watch on your free time to have a look at different open channel flows. So based on the existence of an open channel flow can be natural or artificial. So natural channels, for example, you have rivers, you have canals, valleys, and these are generally irregular in shape, and alignment and roughness on the surface of these channels are also quite irregular. Okay. And then you can have artificial channels built, for example, by people for a specific purpose, such as irrigation or water supply, wastewater treatment, or power development, or rain collection channels. So these are much more regular in shape, and they have much more regular or uniform roughness at the boundary of the surface. For example, here you have much more rough canal bed, while here in this artificial channel you have much more smooth structure, and as such you have less turbulence and roughness. Okay. And irrespective of all these channels, the natural or artificial, the flow in an open channel is due to the gravity. Okay. So for the case of pipe flows, the flow is due to pressure gradient, but for the case of open channel flows, the flow is only by gravity. Okay, there is no pressure gradient. Okay, so now why or how it is relevant to us as chemical engineers. So here I have put an example of a water treatment plant. So for the case of water treatment plant, the fluid goes from one stage to another stage, and if we build these in these stages as open channels and we do it in a smart way, we can actually move fluid from one stage to another stage without the need of having a pump. Okay, so we can move the fluid just by using gravity in open channel. A couple of other examples are, for example, if you have that is for flood prevention, and in case of heavy rains, you can have floods, and we want to get rid of this extra water. So we want to drain the water, so we can design our drainage system as an open channel. And by doing that, we can get rid of this water without turning on a pump. Okay, so this is another use of open channels. uh, Another example is containment. And containment, for example, in case of if you have some chemical spillage, or spillage from a nuclear plant, or whatever kind of spillage. So we can, and you don't want human intervention, so we can design these drainage system. As you can see here, these black lines are actually drainage systems, and if you have any spillage, it will all go to the drain, and that will be collected in an open channel, and then you can treat it there. Okay, so again, you don't need a pump for that, you don't need people to interfere with it, it can just be collected in these open channels. You can have also some other examples. For example, if you, for example, for farmers, it's very important. So, like you have a dam, and with the dam, you have an elaborate network of canals to water your crops. So, for example, this is again an important part of a study of open channel flows, that how to maintain a certain flow in these canals, and how to maintain the level in these canals, so that that there is no deposition of minerals in the canals as the water move in these canals for farmers. Okay, and this all is covered by the concepts of open channel flows. You also have, for example, if you for example, work with mechanical engineers in future, and you work on bridge, for example. So all these bridge have piers. Okay, and these piers sat at the bottom of the, or the bed of the river, and in time the soil around the pier actually become loose. Okay, so you have a kind of a loose structure around the pier. Okay, so we need to know that, and this looseness is called scar. Okay, so this soil scar, we need to know as engineers that when it is going to happen, and what would be the depth of this scarring around the pier, so that we can predict that what will be the effect on the stability of this pier. Okay, so we design our pier depth, or the point where the pier sat on the bed, in a way that the foundation depth, that is this point, is actually larger than this maximum scarring length. Okay, so that is again comes under the analysis of open channel flows. We can also have river morphodynamics, and what that means, that for example, if you have a river here, in time the river change their shape. So for example, from this shape they can go to this shape, and the study of how this river is changing shape in time is called river morphodynamics. And by changing this shape, the river is going to change its flow, and as such it is going to change, or you need to know this information, because it is going to uh, affect the river flood management plan. Okay, so these things are very important for flood prevention analysis. Okay, so these are just a couple of examples that I gave for open channel flows. Obviously, there are much more examples for open channel flows for chemical engineers as well. And for the course of this unit, we have been mostly talking about flows in closed channels that are normally known as pipe flows. And so here I just want to make a comparison between pipe flow and open channel flows, and how they are similar but at the same time different. So for example, one biggest difference between an open channel and pipe flow is that for open channels we have a free surface, while for the case of pipe flows we don't have a free surface. Okay, it means that in a pipe there is no free surface, the pipe is filled with the fluid. Also for the case of pipe flows, the main driving force is pressure gradient, while for the case of open channel flows, the main driving force is gravity. We don't have a pressure gradient, though we have, for the case of both open channel and pipe flows, we have the concept of hydrostatics as we discussed in lecture 2. So if you are in a pipe flow or if you are in a channel, open channel, it doesn't matter. The concept of hydrostatics applies the same. For the case of open channel flow, the analysis or the calculation is much more difficult because, for example, the flow area is determined by the geometry of the channel plus the level of the free surface of the liquid, which is going to change with the flow direction and also as the flow happen in time. Okay, so the area calculation is much more difficult for open channel flows compared to pipe flows where the area is fixed by the pipe dimension. So just by knowing the shape of the pipe, you can calculate the surface area from algebraic equations. Okay. Another reason the analysis of open channel flows are much more difficult because you have much more complex shapes of open channels. You can have irregular shapes, and that kind of increase the complexity of the analysis compared to pipe flows. Also, in terms of materials, you have versatile materials available for open channels. They can be wood channels or concrete channels. They can be natural channels. So a range of materials compared to pipe flows where you mostly have metal pipes. Yeah. And also there can be natural variation in irregular channels, as I explained here, for example, that you can have much more complex shapes for open channel flows compared to pipe flows. And the relative roughness of the open channel flows change in time as well, while for the case of pipe flows, the roughness is mostly a fixed quantity. Okay. So these are some of the differences that are between open channel and pipe flows. And here, that is more or less what I discussed. It's summarized here, so please have a look in your free time. And now, based on the shape of an open channel, you can have two main types, and these are called prismatic channels and non-prismatic channels. So in its simplicity, prismatic channels are channels made by men, for example, or by people, where you have much more uniform shape and the slope of the channel. So for example, this would be considered a prismatic channel, while if you have a channel that is given here, for example, that has a non-uniform surface and roughness, we normally consider this channel as prismatic channels. And most of the for example, most of the natural channels are non-prismatic channels. It means they are not uniform. They have complex shapes. So for analysis, mostly for chemical engineers, we deal with prismatic channels. Okay, but if you are, for example, working on a river or on a bridge development, you have to work with non-prismatic channels as well. Okay, but then the analysis is much more complex compared to prismatic channels. So prismatic channels can be there can be certain shapes. So for example, you can have a rectangular channel. You can have, for example, parabolic channel. You have triangular channel, trapezoidal channel. You can have a circular channel. Okay, so these are the examples of prismatic channels. Okay, as you can see, they are much more uniform in its shape. So you can simply use algebraic equations to calculate their areas and their dimensions and other features. So some of the features or geometry properties that we need for analysis for these channels are given here. Okay. So first term is what we call depth or flow depth. Okay. So the flow depth is the distance from the lowest point, that is the bed of your channel, to the top surface. Okay, so that is y in this case here. Okay, so the vertical distance between the bed and the surface of your channel is what we call flow depth. Okay, then you have the stage z, that is the vertical distance from the free surface to an arbitrary datum. So for example, if you define a datum here, and if you take this distance, that will be z. Okay, so that is just an arbitrary distance from the surface of your fluid to an arbitrary datum. Then you have area, that is simply the cross-sectional area of the channel. Okay, so if you have a rectangular area, that will be the width of the channel times the height of the channel. Okay, then you have another parameter that is called wetted perimeter. So the wetted perimeter is a parameter or is the length of the channel that is in contact with your fluid. Okay, so for example, if you have a rectangular channel here, so you have this length that is in contact with the fluid, you have this length, the bottom length, and then you have this length. Okay, so if you take the dimension from here all the way to here, that is what we call wetted parameter. Okay, and the reason we take this wetted parameter, because this is the length of the channel that is going to interfere the flow due to the friction. Okay, the fluid is going to be in contact with this surface, and that is going to cause friction, and that is going to affect your channel's flow. Then you have another parameter is called surface width. It is sometimes represented as T or B. It doesn't really matter. The idea is that the for example, this length or the width of your channel. Okay, so it can be B, it can be T. Okay, then you have the hydraulic radius. So again, this is a slightly new term, and hydraulic radius is a characteristic dimension of this channel. So for example, a characteristic dimension of a circular pipe is the diameter or the radius, while for the case of an irregular shape, you use hydraulic radius. Okay, so hydraulic radius is the ratio between the wetted parameter, that is P, and the area. Okay, so area of the cross section divided by the wetted parameter. And then you have another related term that is called hydraulic mean depth, and that is the ratio of the area to surface to the width. Okay, so A over T or A over B. Okay, so these are again geometric definitions or coming from algebraic equations. Okay, and for different shapes, for example, you can have different shape of channels. You can have irregular channels, you can have rectangular channels, you can have triangular channels, you can have trapezoidal channels, you can have circular channels. So you need to calculate what are these properties that, for example, I talked here. So you have the area, you have the top width, you have the wetted parameter. So all these formulations come from geometries. Okay, so you don't really need to memorize them. These equations, if you need to solve this, for example, equation, these values or these equations will be given to you in exam. Okay, so you don't need to memorize them. Just try to understand them, how you get them. So for example, simply the area of our rectangular channel is width times the height. The top width is B or T. Okay, and the wetted parameter is, for example, here you can say you have B, that is the bottom, and you have one Y on this side and you have the other Y on the other side, so that is why it's B plus 2Y. Okay, and similarly you can write it for the other shapes. Okay, so all these equations come from geometry. There is no physical sense in from it. They are purely geometrical analysis. So just try to understand them and see how you can use them to calculate hydraulic radius of different shapes. Okay, and we will use it in the next part. So that is all for part one. In part two, we will look at different types of open channel flows, and then in part three, we will look at some equations to analyze open channel flows. Thank you for your time.